Okay, we're pleased now to have John Challis from Penn State University, and his talk is entitled Body Scale and Movement.
Good morning. So when Carl was at Penn State, the conversation we often had was that we should team teach a course on body scale and movement. And then Carl left Penn State. We refer to it ran away, but he left Penn State, and so we never got a chance to teach that course. And when I was reflecting on, an opportunity past, I realized that, to teach the class to an upper-level undergraduate class, you would need a bunch of intellectually curious students that weren't driven to careers in physical therapy, which means it was unlikely we were going to get a very receptive class. But I think this group really meets those criteria, so hopefully this will work well. If it works really well, it was all my idea, and if not, it was Carl's. So what I'm going to do today is, this is sort of probably what would be the review lecture for the final for my half of the class. So what I'm going to do is I'm going to talk about a little bit about background about movement, our interest in movement, and then a little bit about the background, predominantly the biology of scaling. Then talk about scaling in a little bit of a broader context related to movement, and then focus on 3 performance tasks. So, scaling when we try to move faster, scaling when we try to jump higher, and scaling when we have increased strength. And the picture here is Robert Wadlow and his father. So the father is 182, 1 meter 82, so just under 6 feet tall. And Robert is about 2 meters 72, so just under 9 feet tall. So, I think we have an interest in scale, and this is sort of an extreme example of scale. When my lab group meets, we talk about contemporary issues in biomechanics. And I prepared this talk a little while ago. And at one of the lab meetings, I said to the guys, I think I have quite a lot of equations in my talk. And one of them said, well, Albert Einstein said, for every equation you have, you lose half your audience. And I said, well, look, I'm not going to be here next week. And, if you guys, next week when you meet this, you have a paper to review. But when you review that paper, perhaps you could have a discussion and come up with some ideas about how I could sort of get around the equation issue. And so I thought that when I came back the following week that they would have some very clever graphics ways of presenting some of the data and the equations and some sort of guidance for me. And there are the 2 pieces of information they have, or 2 pieces of feedback they gave me, one was, can you tap dance? Because that would re-attract the audience back to, which I can't tap dance. And the second one was, what about pictures of naked people? That would get the audience. And so really graduate students of no use at all. But maybe I'll sneak. I'm not going to tap dance, but maybe I'll sneak in some pictures. So this is a cave painting. It's one of the oldest paintings that we're aware of. It's in France, and it's about 17,000 years old. And when you see descriptions of this cave painting and when it was first discovered, people said, pictures of humans hunting, and which is true. But when I look at the picture, I actually don't see just a picture. I think of it almost like a sequence. So if we look at the animal here, we can sort of think of the animal locomoting along. And if we look at the person here, they're lifting up their bow, they're drawing their bow, they've got it to the full extent, and then they're releasing the arrow. So I think this is a sort of, I look at this as a very early sort of analysis or a depiction of human movement. The technology that we have to analyze human movement sort of eluded us for a very long time, so we were sort of lost with, we were left with using the naked eye. As part of the French military effort, the French funded Etienne-Jules Marey to analyze human movement. They wanted to make the French soldiers more efficient when they went off to war. They didn't really know how to do that, and so they asked Marey to try and work it out, and Marey said, well, we know nothing about human movement, so as a consequence, he just did studies of basic movement. And this is one of the classic images that he has, which shows a stick figure, which is what we now get out of our motion analysis systems, but a stick figure of human locomotion. The next major figure in this is Edward Muybridge, and Edward Muybridge started his career as a bookseller. He then became a portrait photographer. And Leland Stanford had a bet with somebody about when a horse was trotting, whether it had all 4 hoofs off the ground at the same time. And he couldn't settle that bet very easily, but he went to Muybridge and said, Muybridge, you're a portrait photographer, take a few photos of these horses trotting, and then I'll win my bet. And Mowbray said, well, when I take portrait photos, I take the cap off the lens of the camera and I expose the film for 10 seconds. So when this horse was trotting past with that sort of technology, it would just be a blur and you wouldn't see what you're interested in. So Stanford basically set him up on his farm, and he had a mini lab where he was trying to develop film emulsion that would react much quicker, and he was trying to develop shutters that would open and close very quickly. And eventually he captured images such as this. So this is just a sequence of a horse running along. But at the time it was a major scientific discovery. So he toured the world showing pictures, these images, had a limited number of images at the time, but it was considered to be state-of-the-art. When he came back from his world tour after helping Stanford settle his bet, he was employed at the University of Pennsylvania, where he set about cataloguing human movement. And so, I don't know how well you can see this, but these are two people dancing, so it's a naked image just to regain your attention. So there's two people dancing. And so one of the things you see in Mowbray's books is that he tried to capture all the essential elements of human movement. So people dancing, people walking, people ascending stairs, descending stairs, and he tried to catalogue them with pictures such as this. Within the catalogue of his pictures, there's things that amaze me, so I don't think for a blacksmith to be hammering out a horseshoe naked is really a very good idea, but that's in there. My favourite one is horse locomoting with rider. Obviously the horse is naked. The rider is also naked, and at the time that was the president of the University of Pennsylvania. So that would be that type of photo would be one that we should all have if we're looking for monetary increases in our salary. So this is tap dancing. So when we get into the last century, we get the ability to actually be able to record movement and understand about movement. And of course, I think in kinesiology we have a fascination with movement. But then the question becomes, sort of how's that movement generated and how is it scaled? And so we know from physiology about energy sources, we know from biomechanics about forces and loads, but the focus today is sort of the general scaling of that. So Da Vinci was interested in body scale, so this is Vitruvian Man, and so we look at the square, and one of the things he's indicating here is if we take the standing height, so the bottom edge of the square and the top edge of the square, then notice that the fingertips touch the side edges of the square, suggesting that our sort of wingspan is equal to our standing height, and which is, on average, is correct, and so that was a concept of getting at body scale. Galileo was questioned about body scale because when the Italians were finding skeletons of dinosaurs, they didn't believe that dinosaurs existed, so they thought these huge bones they were getting must have come from some of our ancient ancestors that were giants. And so they asked Galileo about it, so he thought about body scale, and he thought about how large the bones would need to be if these bones actually did come from ancient ancestors that were 10 times the size we are. And he was readily able to say, with what we know about human bones and we know about human body structure, it's not feasible that these came from giant humans. So Schmidt-Nielsen sort of summarizes, to my mind, the approach that's taken a lot in biology, or was taken a lot in biology, to try and understand about body size. And if you go to Schmidt-Nielsen's book, although there's a lot of emphasis, there is some emphasis in there on aspects of movement, a lot of the emphasis is about the size of the component parts, so how big is the liver, the kidney, the lungs, and so on. So we're trying to understand sort of what those building blocks are. But of course, we're interested in movement, so then how do the relative sizes of those building blocks influence how we move? So one of the concepts that's pretty common is this idea of geometric scaling. So here are 4 cubes that are all of obviously the same shape, but they're all of different sizes. And then we can look at the length, the area, the volume, and there's a relationship between those. So here one squared is the area of the side, and one cube is the volume of the square. But when we get to this much bigger square, the same sort of principle follows, that the length of one side is 4, the area of one side is 16, so 4 squared, and 4 cubed, 64 is the total volume. So we've got some sort of measure of dimension. So the idea would be that if we know something about a length, we can imply what an area might be by squaring that length, and we could imply what a volume might be by cubing that length. And indeed, again, the general concept in scaling is that the volume is directly proportional to the mass. So we end up with just a bunch of relationships that allow us to sort of try and get some idea of the general scale relationships. And when we think about the lengths, and this is the same with biologists when they're looking at animals, this is when we look at ourselves, it could be a limb length, a standing height, a muscle length, a tendon length. When we think about the masses, it could be the mass of a limb or the body mass or the liver, mass of your kidney or your liver. And then when we think about areas, it could be the total body surface area, lung volume, and so on. The general mathematical relationship here is that we've got some body measurement that we're interested in, so may relate to a length, an area, a volume, or a mass, which is equal to a function of some scaling factor A and then some other body measurement raised to the power of B. So the X here is just some other body measurement. The most common one is the most common ones are the easy ones to measure, whether that's standing height or body mass. And those two are the two common measures that have been used in biology when they're looking at scaling relationships. And then the crucial thing becomes the size of the scaling exponent up here, B. And if you remember your basic math, so we can take the log of this relationship, then it starts to look like the equation straight line. So here's some data, it doesn't matter what the data is, but on a log scale, and then the relationship here has a particular gradient, has a particular line fitted to it, which has a gradient of 1/3, which would be that scaling exponent. So when we do the analysis of these body parameters, then we're looking at how, what type of relationships fit here and what type of scaling exponent we get there. So just to illustrate this, here's some classic data from Pennyquick on some seabirds. So this is the wandering albatross. It's one of the biggest birds. So it has a mass of about 9 kilograms or so, but it has a wingspan of about 3 meters. So it's a huge bird. Not that heavy, but in terms of just sheer dimensions. This is the storm petrel, and the storm petrel has a mass of about 0.038 kilograms. So that's, I'm trying to think of something that has about that mass. It's a little bit lighter than tomato for those of you with English background. So it's a little bit lighter than tomato. So it's pretty small. But this has a wingspan of about 40 centimeters. Remember, the other one was a wingspan of nearly 3 meters. This has a wingspan of 40 centimeters. So we can look at their data side by side. So the mass, well, we'll start with the wingspan. The wingspan is about 8 times larger in the albatross compared to the petrel. If we look at the mass, it's about 230 times the difference. And here are the two birds side by side. But obviously that doesn't give an indication of scale. This is an indication of scale. So the petrel is very small. What Pennyquick did was he collected data on lots of birds, seabirds. And here they are drawn to scale, and then here they are all on the same scale. And his broad argument is that the general shape is pretty similar here. So although we're going from the storm petrel, the smallest one, up to the wandering albatross is the largest one, the general shape is the same. And he measured such things such as their mass and their wingspan and their wing area. And so this is the graph I showed you earlier. So this is the mass of those birds, and here is the wingspan of those birds, both in a log scale. And this is the fit to that data, and it just slightly deviates away from the 1/3 relationship. But so what we would expect from a geometric scaling relationship is that the linear dimension of the wingspan, so length, in relation to mass should be, so the mass should be to 1/3 power in relation to the wingspan, and it gets pretty close. And so that's sort of an argument for the general geometric scaling case. So this is data from Schmidt-Nielsen, and again, a lot of times in biology, the emphasis has been on the component parts of the system. So surface area, lung volume, skeletal mass, muscle mass, heart mass. And then Schmidt-Nielsen sort of gathered these data together and said, well, for the surface area, I'm getting an exponent experimentally of just 1.95. Theoretically, it should be 2. For heart mass, 2.94. Theoretically, it should be 3. So that's pretty good. It's capturing this. And the scale of animals that Schmidt-Nielsen was using is from a shrew, which weighs maybe 200 grams, up to an elephant, which can weigh 6 tons. That's an Indian elephant. It can weigh 6 tons. So a massive scale change. And yet, broadly, this scaling relationship is sort of capturing the basic design features. If we look at some data on humans, then what do we get? Well, for surface area, actually that's wrong. So for surface area, there should be 1 over here. So for surface area, we get a theoretical 0.99, there should be 1. For muscle mass, we're getting 3.1, it should be 3. But broadly, we're capturing the same type of relationship. Now, the beauty that Schmidt-Nielsen had was he had this massive range of scales, from a very small shrew up to the African elephant. We don't get quite that range in humans, and we have a little bit of data on Robert Wardlow, but we don't really have any people between an NBA player and the sheer height of Robert Wardrobe. But what we do see here is that broadly these geometric scaling principles seem to hold. Now, on the right-hand side of the screen, This is a marathon runner, relatively skinny, distressed-looking marathon runner, and this is a sprinter. So, those two guys, they have 2 legs and 2 arms and so on, but obviously there's a scale difference. So the geometric scaling, what it's showing us is sort of the general design. And then the idea is that we can look at deviations away from that design to understand some aspects of specialization. So I say we're not by any means are we all of that design, but we're trying to get at sort of use the scale relationship to understand more about what's going on and then understand the deviations. And so, for example, we can think about how do we move? Well, we move because our muscles are active. Well, the cross-sectional area of the muscle, which is proportional to the force they produce, scales relative to any length squared or any mass to the 2/3. Our moment of inertia, which is our resistance to angular motion. Now, most times in human movement, we actually want linear motion, but we achieve linear motion by angular motion of our joints, so we need to understand what the resistance is to moving our limbs. So that scales to, say, mass to the 5/3. Angular acceleration, which is what gets our limbs moving, scales in relation to mass to the minus 2/3. And frequency of movement seems to scale to mass length to the minus 1. So we've got a bunch of relationships here that, beyond predicting sort of how big your liver or kidney or surface area should be, actually relate to how movement is achieved. So what I'm going to do is I'm going to sort of take the Olympics as a starting point. So the citius, altus, fortius. So I'm going to look at faster, higher, and stronger examples from those. And what I'm going to do there is sort of use mechanics, scaling, anthropometry to try and make some predictions. So these are broad generalizations, and then examining extremes as well to try and get an idea of what's going on. So this is Usain Bolt, so the most bemedaled athlete from track and field in the last decade or so. And the only reason he won more medals than this guy, Mo Farah, is because Mo Farah didn't have the opportunity to run in relays. So they're both very successful across multiple Olympics and across multiple world championships. But they're very different in size. So I don't know how well you can see this in the back here, but so our standing height should scale relative to our mass. So our height cubed should be proportional to our mass. And so Mo Farah has a height of 1.75 m, has a mass of 58.2. Bolt's much taller at 195 and much heavier at 94.1. So my vice versa down here means if I sort of model how tall and heavy Usain Bolt is, and then I say, well, imagine that he was only 1.75 m, then that's predicting, Usain Bolt's stage is predicting that Mo Farah should weigh about 10 kilograms more. Or if I take Mo Farah's data, then it's predicting that Usain Bolt should weigh about 14 kilograms less. So it's sort of getting at this idea of the relative scale between the two guys. So basically Mo Farah is relatively short and relatively skinny, and Usain Bolt is relatively tall, but also relatively muscular with it. And here are the two of them together. And again, you get some idea of the general scale of them. And then, what does this tell us about sprinters and marathon runners? And I know I know that Mo Farah, his success was in 5,000 and 10,000, but he's just about to become a marathon runner because there's more money there. Anyway, so the marathon runners, they have relatively small bodies with low body mass. What does that give them? That gives them a lot of surface area relative to the sprinters, and that's good for heat exchange. If you're running long distances, you need to dissipate a lot of that heat, so the more surface area you've got, the more heat you can generate. You have less muscle, which means you get less acceleration, but that's okay because distance running is actually steady state once you get up to speed. So they're not so good at getting up to speed, but they can maintain that speed fairly readily, at which point they don't need to have a lot of acceleration. And they have less surface area, and generally they have less surface area, so less drag. The sprinters have got relatively larger bodies with relatively higher mass, and that means they've got less surface area, so it's poor heat exchange, but heat exchange is not an issue if you're only running 100 meters. And they've got more muscle that allows more acceleration, which is precisely what you want, because in 100 meters, they're very rarely at a steady state. Most of the time they're speeding up, and as soon as they've reached their top speed, all of a sudden fatigue kicks in and they start to slow down anyway. So there's really not a lot of steady state in sprinting. This is, so Howard Schatz produced some really nice pictures of athletes of all different kinds. So this is Dan O'Brien, who's an Olympic champion in the decathlon. Johnny Graves, an 800-meter runner, and as you probably could guess, the two short, skinny guys either side of him are the marathon runners. So, when we look at these body physics, it gives us sort of clues as to what they're doing. So what about going faster? So this is a little bit eclectic. So we've got a Vitruvian Man from Da Vinci, which we saw before. We've got a Dalmatian running, we've got a wheel, and we've got a ship. And I can sort of tie all those things together to get at, I hope I can tie those things together, to get it going going faster. So here's a wheel going along, and it turns out there's a nice relationship between the sort of velocity at the middle of the wheel, the distance between the spokes, and then the radius of the wheel. And indeed, if we take the rim away from the wheel, we can sort of get at the relationship between this horizontal velocity, and it says the velocity is equal to 2 multiplied by the g, acceleration due to gravity, r, the radius of the spoke, to the power of a half, multiplied by the cosine of theta. Now, if we put our spokes all really very close together, so theta became very, very tiny, then the v is maximized. But it turns out that as long as that angle is sort of less than 30, it goes pretty quickly. If we have a lot fewer spokes than that on a rimless wheel, it doesn't go very quickly. So most of the speed we can retain, even if we only have spokes at every 30 degrees. What does this mean for human movement? Well, so in mid-stance, when we look at the angle between the legs, the angle between the legs and the mid-stance, it varies, but 25 up to 33 degrees are not uncommon values. So 30 degrees gives us a little bit of a clue. So here the beetles down here walking with a nice mid-stance, and here's my relationship. And so hopefully you can see this, maybe not too clearly, but this is Vitruvian Man as if Vitruvian Man is a wheel. So these are the legs, sort of at particular angles relative to one another, and then we can sort of play around with this relationship. And the things in the relationship, so if we have a fixed angle, so say 30 degrees, then that bit becomes a constant. 2 is obviously a constant. So the only things that vary here are the velocity and the leg length over here. So we can sort of rearrange this equation, and we get a sort of characteristic relationship between the velocity that somebody's going and their leg length to the power of half should be equal to some constant. And now this becomes sort of clearer in a moment. So if you're British, then you probably know as you sort of travel around Britain, you see a number of buildings, bridges, and so on, with the name Brunel on. So Isambard Brunel was a great British designer of the Victorian era. And he designed a ship, the Great Western. And the Great Western was a fabulous ship, and it managed to do the fastest transatlantic crossing. And then later in his career, they said, will you make us another one? He said, I'll make you one bigger and better. This is the Great, he was imaginative on names. This is the Great Eastern. And this is the Great Eastern, and this is about 210 meters long. So sort of, what's that, almost 3 football fields long. So it's a very long ship. It's the longest to this day. And it worked and so on, except that the drag that it experienced was so large that basically they had to have the engines running at full power all the time for the thing to be able to locomote. And one of the things about Brunel, although he's a famous British engineer, around about a third of his projects were crap, basically, and ran over cost and didn't function as they were the way they were supposed to. And this ship was one of them. The British Admiralty became very, very concerned about this and said, well, we want to design these big ships because that would make us very effective in war, but maybe Brunel gives us an example here that that's not feasible. This is William Froude, and he's a naval engineer, and basically the British Admiralty government gave him money to build at his house an experimental setup where he could try and understand the drag forces acting on ships. And Froude's number is the velocity of the ship squared divided by the length of the ship multiplied by acceleration due to gravity. And you can see that's very similar to the equation that we got for the wheel. And the idea with this is that Froude, basically in a lab in his backyard, could test model boats and then could say, well, if it has this general shape, if you make it 100 times as big, it should still be good. It should be able to, not that large drag forces, it should be able to move without all the problems that the Great Eastern had. Miguel Alexander, who's a famous figure in biomechanics, said, well, Froude's number looks pretty powerful. And so he collected some data on a whole bunch of animals. So the largest one that he collected data on was a rhino. And to collect the data on the rhino, you basically drive out to where the rhino is and you aggravate it. And then, you're in a truck. So you basically, someone sits in the back of the truck with stones. They throw stones at the rhino. That aggravates the rhino. Then the rhino moves after them. and they use one of those radar guns the police use at those speed traps to try and work out how fast the rhino was going. He also did stuff back, this is, he did this in Kenya, he also did stuff back in his home base in Leeds in the UK, looking at dogs, so Dalmatians. He also had cats, but I'm more of a dog person, so I put the Dalmatian in. So he had cats, Dalmatians, a large scale. And he said, well, all these animals are quadrupeds. They actually have very similar gaits. When I look at their gaits, they're very similar. And he said, look, you know, the walk to trot transition, so you walk and then the Dalmatian or the rhino goes a little bit quicker, and then they start to trot. That happens at a fruit number of 0.5, so obviously it's probably going to be a much higher velocity for the rhino, let's say, than the cat. But we can scale it with this v squared divided by leg length. And then the trot to gallop transition, that's when you've really aggravated the rhino because it's now chasing the trot. And then in that case, the transition happens at fruit number of 2.5. In human movement, what do we see? Well, here's somebody walking along with a child, and if we see that, maybe in a supermarket or at the beach, we notice the child is moving really quickly, and often the parent is moving relatively slowly. They're both walking, but one is working much, much harder. Here's some data of a bunch of children and a bunch of adults. So the child is walking, could walk as slow as about 0.4 meters per second, and as fast as 1.5 meters per second. But the adult found it really hard to walk much slower than half a meter per second, could put walking speeds up approaching 2.5 meters per second, and this is their stride length. So we're looking at the relationship between their velocity and the stride length. So can we scale those two? Here are the results. Here are some results of that. So this is the adult data and the child data, and we've divided through by height. But they still don't really sort of match one another. But if we take the Froude relationship, that scaling relationship, we see that the Froude's number here, when we plot against stride length divided by time, then the two curves overlie one another, suggesting that if we use the appropriate scaling, we're saying they are doing the same thing, it's just that we need to allow for their body scale. So what about jumping high? So I think you could all pick the high jumper out of this picture. So why, what do high jumpers do? Well, high jumpers perform muscular work to jump high. So muscular work is the product of the force your muscle produces multiplied by the change in its length. Well, that turns out that the force is proportional to the mass to the 2/3, and height, the change in length of the muscle is proportional to height, which is also proportional to your mass to the 1/3, which means in actual fact the work you do is proportional to the mass, and when you jump, your body gains potential energy when you jump. Well, potential energy is just your mass multiplied by acceleration due to gravity multiplied by the height to which you raise your center of mass. So I can say, well, the height is the potential energy divided by the mass, except the potential energy I gained was really just due to the work my muscle produced, which means that my jump height should be invariant irrespective of size, which sort of doesn't work with intuition, except that the high jumper was the tallest one. So what does that mean? It means that if you want to jump high, everybody, in theory, on a scale model, can raise their center of mass the same, jump it up the same height. So the person that's the best is the person who has the highest one at the beginning. That may sound counterintuitive, but let me just show you some data here. If I look at this relationship, imagine the person gets heavier. And so we add mass to the person, how would their height change? Well, what the theory suggests is that their height should change in a sort of somewhat linearish fashion in this way. So this is mass added, and then how the jump heights decrease as we've added mass. We take a group of subjects, we add mass to their bodies by having them jump in a weighted vest, and lo and behold, we get the same type of relationship. So although intuitively we say, really? Of course, some people have more fast twitch fibers and ideal limb lengths, and they jump much higher, but on a scale issue, we all in theory jump the same. Which of course is relevant when we think about people, when we're jumping over a puddle. If we're jumping over a puddle, other than our initial body configuration to get over the puddle, our ability to jump up over the puddle, in theory on a scale model should be equal for all of us. So what about strength? So this is Alex Serf, 72-76, Olympic champion. So this is the weightlifter in the middle here. And I don't think his sort of slightly overweight features are important, but the size of his thighs are probably very important here. We can make a similar argument about when we lift the weight, it gains potential energy. The subject does muscular work, and then we can equate those two. And in the interest of time, it ends up that the mass of the bar we lift is proportional to the mass to the 2/3. Is that true? Well, look at this is data from Olympic weightlifting. So we take the total mass, the Olympic weightlifters, the world records in each of the weight classes. So these are the weights of the athlete, or the masses of the athletes. This total mass they managed to lift, and we get this sort of strange little relationship here. But if we put it on a log-log scale, we can fit a straight line to the data, and we get a scaling exponent about 0.66, which fits in with, that 2/3 the mass the bar you could lift should be proportional to the 2/3. Interestingly, the biggest outlier above the line is this guy here, and this is Nyam Sulimalangolu. He's considered to be one of the greatest weightlifters of the last century, and on this relationship, arguably proportional to body weight, he's the strongest. The gymnast here is the smallest. We think of gymnasts being small. Why are they small? Well, they're small because relative to their body size, if we think about strength being proportional to the mass to the 2/3, they've got the highest relative strength, and they've got relatively the smallest moment of inertia. So, gymnasts are small because higher relative strength, smaller relative moment of inertia. So they can accelerate their body, and the acceleration they get gets rotating faster, and they've got greater strength. The male gymnast is the one in the middle here. This is a basketball player. This is Edward Muybridge. This is my last naked picture. This is Edward Muybridge getting up out of a chair. Although he looks like an old man getting out of a chair, I think he's only in his early 50s here. It turns out if we take the extreme elderly and we get them to stand up out of a chair, they're using around about 90% of their available leg strength. So that's so if you went into the weight room and I said to you, stick this bar on your back and squat down and then stand back up again with 90% of what you can handle, you'd say, well, okay, I did it once, I'll wait another week before I do it again. Except that obviously in an everyday living, we need to get up out of a chair every time we need to use the bathroom, every time we want to go and eat, and so on. So it turns out that the taller and heavier have shorter lifespans. Now, I sort of intuitively I know that because every time I see my parents, they're older, and they always seem shorter. So I think that, yes, yeah, okay, thank you for that one. But there is WHO data, World Health Organization, showing that generally the taller and heavier have shorter lifespans. Well, if we think about how that relates to an activity of daily living, if in the elderly, some of the elderly, we're using 90+% of our available leg strength, the smaller you are, the higher your relative strength is, so therefore the more easy activities of daily living become. Okay, so just to go back to Schmidt-Nielsen one more time, size is one of the most important aspects of animals' endowment, yet size differences are so obvious that we often give them no further thought. I think we give them no further thought often in human movement. Gymnast, weightlifter, and basketball player. Okay, thank you very much for your attention.